Hmm. Great. So let's start the class today. And what do we talk about it? Today we talk about, we are continuing iterative methods in combinatorial optimization. As I mentioned, these are the slides by R. Ravi, who presented several years ago here. I'm using the same slide. And as I mentioned, they also have a book here. This is the book that I think it is freely available. If you search it, that's a beautiful book as well. Not a very long one, it's a short one by Lapchila, Mohit Singh, and R. Ravi. It's a nice book that it talks about this one, but here essentially I'm talking some of the most important problem that we can use using this iterative method. So what is the idea? I'm just giving some things here. Okay, let me bring this rank lemma. Good. Okay, so what is the idea of this thing? So we are writing an LP for a problem. When we are writing the LP, we will consider the basic feasible solution or an extreme point. These are the same things. And then we want to say that in the extreme points, either all these variables will become integral, or there is one variable of, say, at least half, or like half integral, or higher, essentially. We can round them, and then we can continue. And the idea is that at any time, either we will round some variable or we will relax some conditions. So we will relax these conditions, and then we will go ahead essentially with this procedure until we are done. The main thing that we talk about this lemma and the proof of this is this one. That let's X be so this is the one that we are using again and again. This today, this is the rank lemma. That said that if is a P is a polytope, essentially X prime are the variables and X prime are greater than 0, and X be an extreme point solution in P. So X is a solution here, which is an extreme point, or it is again basic feasible solution. Then any maximal number of linearly independent constraints that are height at X. What's the meaning of, so you are writing some of these constraints, AI times X greater or equal to P. Essentially, that means that A1, X1 plus A2, X2 is equal to, I don't know, say, for example, B for some variable, this one. This is called the tight constraint. Versus if it is, this is like greater than this, it's not a tight constraint. And as I mentioned, all this problem that we are talking about are packing constraints. Packing means that all the constraints are greater than or equal. This is an important open problem. Can we apply this one for the, sorry, these are the covering LPs that means that this should be covered. This should essentially like set cover. You should cover this element, should be greater or equal. So this is the covering essentially. This is open problem, as we mentioned at the end, for packing LPs. With a packing LP, you can use this idea. This is the idea for covering LP. We solve the problem. We are just using a regular solver, Groupie, Cplex, or Pulp. They generally give us a basic feasible solution. And we want to say that in this basic feasible solution, either all of them, all the variables are essentially integer. It means that we are done without solving an integer linear program. We just solve a linear program, which is very fast and give us a solution. Or we want to say that at least one of these variables essentially large enough that we can, like 1/2, we can make 1/2 1, and then we are paying a factor 2. As I mentioned, sometimes we may relax some of these things, and then we need to essentially solve this LP again and get the solution. And then, but anytime we have some progress towards solving this problem. This is the general idea. And this one essentially comes from the fact that, here, this fact comes from why do we have this rank lemma? Because the column rank of the matrix is equal to the row rank of a matrix. That's essentially the main things. For this. Now let's go and see the examples. And we talk about the general approaches here. So these are the typical things. Hopefully, if we can cover them all, that would be great. I want to talk about some iterative relaxation and some essentially for several problems here: assignment, generalized assignment, minimum spanning tree, degree bounded spanning tree, and hopefully like this is SNDP survival network design problem, and I mean talk about some open problems. And these are from several essentially some of the best papers in the essentially the field. These are lots of them are JCM papers, and some of them are simplified. These are like state of the art in network design. Super important. Lots of these proofs are proofs from the book. Beautiful proofs, essentially. I try to mention the details as much as possible, but there are some small things that it may remain. You can just read essentially the book by Lapchila, Aravi, and Moit Singh. They explain the things there, or you can just see the papers as well. But you should be able to get the general ideas here, and these are beautiful. Again, these are some of the proof from the book in network design. Like, for example, I also mentioned for group Steiner theory, a simple proof. That was another proof essentially from the book. Like the original proofs are very complicated. These are like a very nice and simple ones. Let's go this one. So let's start with this example. Assignment problem. What is assignment? So you are given a complete bipartite graph. And for each edge, essentially, so this is a bipartite graph. This is bipartite matching, essentially. And say the size of them are both are equal to n, and each edge has some cost, essentially Cij. And you want to select some of these edges, which is a matching, essentially. You want to, here, this is the minimum perfect matching. So you want to minimize those edges that you are selecting their cost. And what is the thing is that you want for each, essentially this is A and B, and you want to make sure that the degree of each vertex in A is at least 1, and the degree of each vertex in B is at least 1. Because that's the definition of matching. And important thing here is that we just say greater than or equal to, we don't say equal to 1, but generally because we want to minimize, do minimization, generally should not go above. You can always show that it would be equal to 1 at most. So I don't put the equation that should be equal, just say greater than or equal is enough. And you try to minimize this. The main thing is that extreme points, X star, generally we say extreme points or basic feasible solutions of the above relaxations are all integral. So you don't need to solve, I mean, we know that essentially this is the weighted bipartite matching. This actually shows that you can actually solve it. And if you want to do maximization, you can do some tricks here, essentially. You can just, instead of, you can change the weights, for example, from Cij to minus Cij, and you can solve the maximization version as well, or some other variants. Okay, we said that you don't need to solve an ILP integer linear program. We don't need to relax this one to just say that Xij should be 0 or 1. If you just say that the solutions are already good. Okay, so let's go this one. This is essentially a state of the art to prove this one. So what is the claim? The claim that at any extreme point X star, there exist edges Ij, which are Xij is equal to 1. So generally, this is the case. So you can say that in these LPs, we will get these ones. Either there are some Xijs. So there are some Xijs that some of them are become essentially 1 or 0. These are the good ones, or sometimes 1/2. Sometimes we have some constraint that we will essentially relax it. But this is also the idea that sometimes you don't need to solve the LP. You can actually consider when you solve the LP one time, you can actually continue with the same LP because everything is integral. And that shows that not only one of them which is integral, but all of them essentially integral. So you can continue with the LP, but sometimes you may need to resolve the LP, the new LP, and then again apply this theorem again. So you can, I mean, this is some details that you can see it for lots of cases, actually, you can continue with the same LP. You don't need to resolve it, but in the worst case, you can actually solve it and then get it. Yeah, you don't need to resolve the LP.
The one question, so in this case, I thought you said that X star is already integral.
No, I want to prove that.
Oh, so you don't prove, okay.
Yeah. So that's the whole thing. I mean, it was known by other things. We are essentially but we are doing that. So to prove the theorem, as I mentioned, apply the lemma repeatedly by deleting match edges and its endpoints, including in the solution, and then resolve it or resolve it. The idea here is that actually you don't need to resolve it. You can just continue with the same LP and several things. You can do that, but that would be one idea essentially to do that. And generally, if you make essentially one variable 1 or 0, then you know that this is in the solution. So if it is in the solution, you know that these guys are matched, so you can just delete them and continue with the rest, essentially. That's the LP that we are writing. This is also the case. When we have, this is also, yeah.
In terms of algorithm, you just run the LP once, right?
You can, I mean, yes, I mean, lots of these cases, one is enough, but in the worst case, you can run it several times. But that you can see different case by case, you can consider it. If we can do it once and then go with that, that is preferable. But sometimes it may not be easier to analyze the other way. Okay, so now this is the case. How can we remove, this is the case. Also, generally, if it is integral, we can do that. This is another important thing. So here we are talking about if this guy is matched with these guys, then of course we will put it 1 and then we will remove both of these guys and then we will do with the rest of it. Another thing, it is also interesting, and we are using this fact again. If sometimes we are doing actually this one, if this guy is 0 between A and B, the XE of this guy is 0. Also, I can remove this edge. I remove this edge from consideration. Why? Because this edge, LP didn't put anything there. It means that the optimum solution didn't need this edge. So I can just delete this one and then go with the rest of them. So sometimes I'm also deleting 0 edges. Sometimes I will put 1 or half integral, means half ones there. I will make them 1 and go there. Sometimes I will just delete 0, guys. Both of them are essentially the case. So even if I want to solve the LP, I mean, if I want to continue with the current LP, of course, this is 0. But if I want to continue with the LP, I know that the optimum solution puts 0 here. So there is a solution that says 0 there. So I just delete this edge and the continue.
Okay, one question. So just because the LP doesn't put, like, if you consider the original problem, it's an IP, right?
Yes.
So just because the LP, let's say an edge is a variable set to 1 in the LP. I mean, if all of them are set to integers, then I can see why it's set. But if you have a solution where one of them is, an integer, doesn't mean that in IP that one is
yeah, I can find a solution which is equal to the LP value that guy is. Yes.
Okay.
The value is the same. Or I mean, like for example, if I get it 1/2 times that, I can just guarantee that anytime I will just pay, if I don't need to resolve the LP or something like it, or even if you want to solve it, you can just make sure that I will, at any time, I will pay essentially 2x the cost of the LP for that variable. And you can sum it up. Good. So let's consider this is the main approach essentially. Consider the support graph. What is the support graph? The support graph is a graph of edges with non-zero values at extreme point x star. So I will solve this LP and it gives me some solutions, correct? Some of them are non-zero. And the issue that non-zero, because the 0 guy, as I mentioned, I can remove them essentially. And these guys are, of course, if they were 1, also they could remove it. So everything x guys here are something between anything, the value of this guy that I get it is between 0 and 1. Strictly. Good. So, and I'm assuming that there is no one edge. One edge means that essentially the edge that has 1, because otherwise it was correct. So I will get this I will essentially get a contradiction by this rank lemma. This is what is the lower bound. I will say lower bound is the number of edges in the support using property of no one edges. These are the number of variables that I have in the solution, correct? These are exactly the x's or my variables which are non-zero. Upper bound is the number of independent constraints that are tight at this point. Good. So lower bound is the number of variables, means that essentially number of edges here. Always I'm doing this. What is the upper bound? Upper bound is the number of independent constraints which are tight. This independent is important. We need to talk about it. Independent constraints that are tight at extreme point x. What do I show? What do I show is that I will show that the lower bound is greater than upper bound. That's it. That's essentially the contradiction that I will get. I will say if there is no one edges, I can show that the number of the lower bound is greater than upper bound. Done. Why? Because this is the extreme points. I know that the number of variables here, which are the number of edges, should be equal to the number of type constants by the rank level. That's always the case. I will generally, lots of them actually, we are talking about the XE. It means that the number of edges which are not integral, essentially, or like this, sometimes 1/2, but lots of them are non-integral. Those edges that I cannot round them, essentially, I will show that these numbers essentially is less than the number of constraints that are tight, and this is a contradiction. That's the whole proof in this talk. So these are essentially, like you see, when I write it, essentially, what is the meaning of that? So what are the constraints which are tight? So the issue that I have some constraint which is tight. These are some equations. A1, x1, x2, x2.
What were the constraints in this problem?
The constraints for these problems are so these are the constraints that I'm talking about. When I talk about the constraint about this, essentially these two type of constraints that I'm talking about. These are the ones. In some sense, these other type of things I will consider, but because they are greater than 0, these are not tight for them. So I'm talking essentially about these guys. But generally, these non-zero guys are the one that I'm talking about. Good. So this is essentially lots of them. The whole problem. We are using actually quite a bit of linear algebra here, the nice linear algebra. But at the end of the day, it's just some counting argument that why this is the case. And so in some sense, lots of them are existential type of things. I don't need to do that. The algorithmic part is easy. One variable, which is 1 or 1/2 or something that I can round it. But see, why is it the case? This needs a proof, essentially, or makes the proof. Good. So this is the global counting argument. So what is the idea here? We know that every node in A, so this is A and this is B, correct? We know that every node in A has essentially has degree at least 2. Good. Why? Because as I mentioned, so each essentially, I think this was not maybe written correctly, but this is the idea as I mentioned. So I know that consider essentially A. There are n variables. So I know that none of these guys are integral, correct? Or everything between 0 and 1. And I know that this should be at least be equal to 1 or at least 1. Good. So what's the meaning of that? It means that each vertex should have at least 2 fractional edges. How many edges should I have in total? I have n vertices here. Each of them should have at least 2. So I should have 2n edges. 2n edges are the number of variables that I have. Now, I only need to say that number of constraints that I have that are tight should be, number of independent constraints that I have which are tight should be less than 2, and I'm done. Why? Okay, so these are the constraints that I have it. This xij is equal to 1, bij is equal to 1. Good. N constraints here, as I mentioned, the size of A and size of B are equal to n, correct? So n constraints here, n constraints here. So far, I don't have any contradiction because I have 2n constraint tight and 2n variables. But there is one thing. These two set of constraints are not essentially independent, because the fact that this set of constraints that essentially when you write this one for all set of variables in A minus the variables on B, that becomes equal to 0. Good, because this one says that the degrees of this guy is essentially this one. I can the fact that some of the this is the things you can write both these constraints for A and B and then sum it up or like minus, and then it becomes 0 because the constraints for A implies the constraints for B. Tight constraints for A implies the tight constraints for B. But we can just write these equations, and we know that this is essentially. So it means that I don't have 2n tight constraints. I can have at most 2n minus 1. Contradiction I'm done. So it means that essentially it should be all of them essentially. One of them should be 1, but if one of them is 1, you can repeat this one now with the same LP because the value of the LP does not change. And this should be an optimum solution for the rest. So you can actually continue with the same LP. And you can show that all of them actually should be 1 in the same LP that you. So this is one example that you don't need to resolve the LP actually, or resolve the LP. So that's all the arguments that we are doing. And this is like, it becomes beautiful later on that what is the things. So only you need to see what are non-tight constraints. You get one of them out, one out, we are done. So let's go to the a bit. This is another, I think it was the JCM or SciComm. This is a very important result here. This is the generalized assignment. What is the generalized assignment? This is some scheduling problem. So this is you have a bipartite graph. You have some jobs and some machines. So these are the some of the jobs, and these are some machines that you have. Because these are the jobs that are machines. Good. You want to assign, this is a typical scheduling problem. You have job J and the machines M. You have a processing time. Pij means that the processing of the jobs on machine. This is the processing of job I or job job J on machine I. So I is the machine, J is the job. And there is a cost for it as well. So it's a very general problem, essentially important problem. So, and this problem is, so what do you want to do? You want to find the minimum cost schedule with make span at most P. Good. So you want to make, so this P currently is P is the same sign. So you want to say that if there is such a thing is possible, and this problem, by the way, is NP hard actually, so you cannot get solved it exactly. But if this essentially is possible that you can assign this one, then I mean, you can even think about the cost is essentially like equal to 1 even, or the cost is not that important. Just even the feasibility question is interesting. What do I show that? I want to show that if I want to minimize this one, the cost, if there is a feasible schedule that you can do everything at most P, then you want to make sure that you will minimize the cost. But the feasibility is itself also interesting, and we can just talk about feasibility. Yeah, go ahead. It's problems that we have.
The feasibility.
The feasibility. Oh. What do we get here? We say that if there is a solution, I can get a 2 approximations.
But feasibility when they're integers, right?
What do you mean integers?
Does xij need to be integral?
Yeah, they should be integral. Yeah, of course. I mean, the other one, this is the LP. Okay, so these are, I mean, some of the things, I mean, I try to give the general ideas, some small thing that I may, if I want to go to the specific things, I mean, that may take time essentially, but you can just read it essentially, but the general idea, how do you do it? These are small. If you know the general picture, then it is very easy to figure out those small things. I try to cover as much as possible, but because I want to cover lots of them, these are all interesting and beautiful things. And these are all of them were very hard problems. The people essentially worked for, I don't know, for several years, 20 years until we got such kind of, it was, the original papers were not that easy at all, but these ones are essentially beautiful proof. Good. So this is the LP. What do we do? Again, do the same thing. So at first we are doing that. We are pruning edges. Those edges that the Pij is greater than P. I say P I'm just using as two things, both as essentially P here. Essentially, I'm considering it sometime that is essentially a vector of all P. So that the P is currently, that may change during the algorithm, but for now is that I want to do it everything at most P. So this is P essentially. Both of them are using P essentially by abuse of notation. So I know that I will first prune the edges which are Pij is greater than P. Why? Because if it is Pij is greater than this job cannot be assigned to this. So I just remove those edges. If this is possible, then that should be the case. Now, I will say if an optimal solution X prime has one edges, then the problem, so, okay, but what was the LP here? Let me just mention the LP again here. So the LP here is about the natural one. It's that I want to minimize the cost. Each job should be assigned at least one. And the total processing for each machine should be at most P. So here, in some sense, this is actually a packing constraint. We can handle these packing constraints here. So sometimes we can also do it, but more of the covering things. Let's see what is the good. So essentially, I have this one. I want to just count the number of edges. At the end of the day, everything is counting. Or double counting, actually, is a better way. Okay, so those edges greater than P, I just removed. Now, if an optimal solution X prime has a one edge, then what's the meaning of one edge? Means that this job, essentially job J, is assigned to this machine P. Then what can this machine I say? Then in this case, what can I do? I can just assign this job J to machine P, and then I will just essentially reduce this because P is called make span. The make span of it was P. Now I will essentially make it P minus P of Ij. This is a new constraint that I will put it because I know this is one. I will just assign it fully and then I'm. So that is good. If X prime also has a zero edges, I just remove it. Good. So essentially, this is again going back to the same thing as before. I have some Xij's here now, which are all between essentially 1 and 0. If it is 1, I can have a progress. 0, I can have a progress. And then in the middle, this is the issue, is the middle part. So this is thing. So if there is a machine with degree 1 in support, what's it mean? So now what is the degree? The degree of each vertex is defined in terms of x is. Those edges that the x is between 0 and 1 are these guys. So if there is this machine I that its degree is 1. So here I will just do this Xij things. And this Xij, as I mentioned, is between 0 and 1. But there is only one job, essentially, one XE that is attached to this I guy. This I is the machine guy. Then in this case, I will just remove the condition for I. Why? Because this is a single job. If it is assigned completely, so here I know that his Xij is essentially less than 1. But I know that if this guy is fully assigned to this guy, the Pij is less than the processing time of this by definition, because otherwise I removed it. So in some sense, actually, I can just this job that is assigned to this, maybe partially assigned to other things, but I can assign it completely this guy to this guy. Because it's partially, there is no one else is assigned it. I didn't use this I for anything else. So in some sense, you want to say that LP has done a wrong things here, but maybe it is another optimum solution can assign this one. But here, in some sense, Xij, if I can, there's only one guy that is attached to this guy. And then I can, and it is between 0 and 1. Why don't you essentially assign J fully to this guy? I don't have any problem with the processing time, because the processing time, I know that the processing time is less than the makers. So if there is such kind of Xij that only essentially one of them is assigned to this, then I can just relax this condition and say that I essentially so this single job using it fractionally cannot have this one. So you can remove the make span constraints. That constraint, that particular constraint that says that this guy should be less than or equal to P, I know that it will not be violated. Good. If I can actually say more than that, if the degree of this guy is 2 fractionally, if machine with degree 2 is in the support, then you can remove its make span constraints as well. If there are 2 guys. However, here, this is the part that I'm giving the 2 approximation. Similar argument to this one that I have mentioned, that if you fully assign this guy, it would be P. You say, okay, if I remove these constraints, the constraint that essentially the make span constraint, that some of these guys assignment to this guy should be at most the processing time of P of this guy. If I remove it, then there are 2 variables that are maybe Xij and another Xij prime essentially as assigned to this. These are the only non-negative ones. I would say that if you remove it, essentially, the LP can assign, instead of 1 guy, it can assign 2 guys here fully. What would be the running time of this? What would be the total running time? Instead of P, I will get it 2P. This is the factor 2 that I mentioned I'm using in approximation. Good. So I remove these conditions essentially from that. Why removing conditions are important? Because the number of constraints become less, the all possible number of constraints. So I will do these things. But what was that?
How do you know that once you remove the constraint, other people don't here?
Okay, one way essentially to do that, as I mentioned, you can just maybe assign these 2 guys to this guy and just remove that guy.
There's no other constraint.
So the idea is that the other guys, they didn't. So just consider the case of one case.
For one, I'm fine.
For 2, a little bit more details, but that is the intuition. That needs a little bit more details. But this is somehow the intuition essentially. But you can just do that, or you can, as I mentioned, you can potentially assign both of these guys to these guys and done, because this guy had essentially thing that I'm losing in terms of approximation. But yeah, this part needs a little bit more things, but this is the general idea. But you can remove these guys for the 2 guys. But here, instead of we are removing, but note that we are losing in terms of approximation factor. And that's essentially the best that you can do it, actually. This is a factor 2 is the best that you can do it unless P is not equal to NP, if I remember correctly, for this problem. So you will do this one. Now let's continue. Now, this is actually the things that they have it. So we said that for any extreme point, either there exists a make span constraint to relax, means that that's the one that I mentioned, or there is a one edge. So we will apply this lemma until we are solving essentially the whole problem. This is actually the great result of Shimois and Tardosh in 93, that generalized assignment LP can be rounded to give a solution with optimal cost and make a span at most 2. This is a factor 2. And as I mentioned, you cannot get better than 2 actually. I think that's the hard. Unless P not equal to P equal to NP, you cannot get better than 2. Now let's go and see. We have not finished the whole thing yet. Let's see this one. Good. So just again, essentially the same argument that we had. It's the counting argument. So consider this essentially Xij's. What did I mention? I mentioned that it is essentially job J, and this is the J's, and this is jobs, and this is the machines. I know that, what do I know? I know that the degree of these J guys and all these X's are between 1 and 0. I know that the degrees of these guys is at least 2 because they are fractional. The degrees of this guy, because of this constraint that I removed it if it was at most 2, the degree of this guy would be at least 3. Good. How many edges do I have? The number of edges, the sum of the degrees over 2. 2 times the number of jobs plus 3 the number of machines. Over 2. I'm just summing up the degrees. But how many tight constraints that I can have? Essentially, the jobs plus the number of machines. Because there are all possible set of constraints that I have. So contradiction, because this is great. That's it. So their proof is much more complicated. This is actually much nicer. Again, this the only thing is that that 2, the rest is like essentially solid.
This is the new proof for that result.
Yes. Those are very complicated. These ones are much easier. Essentially, they became trivial. This other one, let's go to the next one. Oh. Good. Let's go to the next problem. So this is the, this is the, like essentially the one that we are mentioning. Let's go to the degree bounded minimum spanning tree. What is the degree bounded spanning tree? So this is the thing. So given a graph with cost j in integer k, find a spanning tree with maximum degree at most k. But again, if it exists, it finds it essentially for you. But k can be the same or it can be different. For different edges, you can have a different constraint. That is fine. So you can actually, more general, not only upper, or you can even solve when they have upper and lower bound for the edges. You give some approximation factor, but that's it. So note that for k equal to 2, this problem is the Hamiltonian path. So k equal to 2, if you say that the degree is at most 2, then you want to find the Hamiltonian path in the graph. And this Hamiltonian path I mentioned previously, and this is actually NP hard. So if you don't want to relax, there is no approximation for this problem. You need to relax it. What is the relaxation? I'm saying that if there is a solution, that essentially has at most k, I can find a solution that has at most k plus 1. And again, you can say that whether there is solution of size at most k, because you can try all of these possibilities, the approach that I mentioned, find the solution is the valid. So if it is valid, if there is a solution, then it means that the LP should be essentially a feasible solution. And then essentially I will get 1 plus the LP, so it is a stronger part. So all of these are like this, that if I don't relax, I cannot solve it, essentially, any approximation. Like even for the previous one, generalized assignment problem, I will solve it, I will get these different things for different P, essentially. If it is not feasible with P, there is no solution, then I don't get a correct solution. But if I find the correct solution, I will take the minimum of those guys. Always this would be the case. So this problem, essentially, as I mentioned, this is NP hard if you don't relax it, but let's see this one. Good. So let's write this problem. This is the constraint that we can write it for this problem. So how can we write a minimum spanning tree LP? So you can actually generalize this one even for a Steiner tree. You can just do that. But this is essentially the thing that I'm doing that. So if there are some generalization for Steiner tree, but say here it's a spanning tree. I want to find a spanning tree, bounded degree spanning tree. But I need to understand 2 types of constraints. First is this constraint that what would be the LP for minimum spanning tree? That one. And then that would be easy. Then I will say that the sum of the variables that are attached to each vertex, because each edge is xe that is attached to it. Some of them should be at most k, the degree of this guy. Good. So let's start with minimum spanning tree. So let's write the minimum spanning tree. So a spanning tree polyhedron. So this is a linear programming relaxation that you can write it for. I will say that this is the minimum. So again, xe means that this edge will be selected or not. I will say the sum of the cost I want to minimize. I want that the number of vertices, the number of edges should be n minus 1. That's a trivial one that we know. The other one is this one. For any set S, sum of the x's should at most size of s minus a. Good. So for any size, for any essentially s, the number of edges inside should be at most s minus. And that's it. So this is so far for a spanning tree. So this essentially, it was shown that the extreme point. So this is non-trivial. Why this is actually a solution for a spanning tree. You can actually get, so these things, the number of constraints here are exponential, but you can actually solve it using ellipsoid method, because you can do essentially you can find the violated, this is called the separation oracle. You can find a condition which is violated by a separation oracle in polynomial time, and then you can do it using the ellipsoid method. So solving it is not trivial, but say we can solve it in polynomial time. The issue is this one, that we get this solution, why this is integral. And this is the one that is essentially, again, proved by great Edmonds, essentially, 71, that this one all integral if you solve it. It is completely non-trivial why it is the case. I will prove that essentially first here, and then we go for the next one. So this is the important one. This we are using a lot in all of this. So independent set of these tight constraints can be chosen such that I have a laminar family. Good. So what is a laminar family? Laminar family is this one. Essentially that this constraint that I have it, they form essentially a laminar family. It means that laminar family means that there is no proper intersection. So no two sets A and B that they properly intersect. Each two sets that we get it, either they are disjoint, so no such things. Either this or one is inside the other. Essentially, laminar means a hierarchy. Now, this one is essentially important that I will talk about. This is a standard called a standard uncrossing argument. I will mention that so that you have some ideas about it. So what is a tight set? Tight set is the one that sum of essentially, what was the condition? We said that for any set S, the sum of xe should be less than, this is the condition that we have, correct? This is the condition. So of course, for all the edges, I have this one. For V, I have this one. But for any set S, I know the sum of x is less than size of S minus 1. So it would be tight if it is exactly equal. So x of E of A means sum of the x's for all edges in A. So a tight constraint is that the sum of the x's is equal to the size of A minus 1. Good. So this is the one essentially, it was again done by Edmonds. This is actually a very important, interesting thing that is done there. It's still non-trivial. That shows that this kind of tight constraint, they should form a laminar. Or there is a set of tight constraints which are independent and they will form essentially a laminar family. So there is an independent set of tight constraints that form a laminar family. Maybe there are some other independent sets, but they can form essentially independent set that they are forming a laminar family. So let's see what is the proof for that. So this is the idea essentially. You can say if we define x of this, x again, x of something means that sum of the x's of those edges. Essentially, this is I think this function that they have mentioned is submodular. This f function, the one that essentially sum it up over this x function. This x function is a submodular function. How you can do it? Just do it essentially. That is a simple argument. You can do it. You just do it using not this definition of submodularity, the other one. That if you are giving, so if I have essentially, so this is important. I will define x of, you see, I define x of E of A. Or I can just say simpler, X of A. What is X of A? It means that all edges that exist, both endpoints are in A. I will just sum up the X of that. Good. So this is actually is defined on A. So this you can't just define it instead of this one. I will just define it on X of A. This is some because now I've defined it on the vertices. This function is a submodular function.
Both endpoints are?
Both endpoints are.
But then if you have, let's say you take one vertex.
Yeah.
So this will be 0.
Yeah, I don't talk about, so that is not a valid thing. I need to have at least 2 vertices. Okay. So in my laminar family, I should have at least 2 vertices.
So I'm putting something else, like I feel like it should be super modular. It's like if you have one vertex, then when you calculate x of e of a, it's going to be 0. When you add the second vertex, it's going to jump to 1. I feel like it should be one endpoint, not both.
No. This is for just one endpoint. This is for both endpoints. The only thing is that it's either I think it is submodularity or supermodularity. That's the thing that I.
So they should, like when you add a vertex, it might not, the edges don't come yet. It's like you're making some edges ready to join later when you add the second vertex.
Yes, but this actually this one that we are considering, I think we can define only on the set of sets that they have at least 2 vertices.
Yeah, but even if you do 2, it kind of still remains like let's say you have 2 vertices, right? It's like A and B, and there's okay, there's 2 other vertices, C and D, right? Now C is connected to D. When I add C, nothing's going to happen. It's like that edge is going to get added, right? When I add D, still nothing's going to happen. But if I add C and D together, something will happen.
Yeah, so this part I think we can do by case analysis. We can discuss that one. Because as I mentioned, also I need to check it whether it was with submodularity or supermodularity. But anyhow, this can be done essentially for this part. But yes, but I'm sure that is the X of E is actually is the meaning of that is the because let me just see that what is the one that we are defining here. You see, here we are defining E belongs to E of S, set of edges at both endpoints in S. So I think there might be submodularity versus supermodularity, but you can check this one. Anyhow, this is correct, essentially. There is something that can be done. But what is the general idea, essentially, here? So what is the general idea of uncrossing? This is a very important one that is used actually a lot. So say we have this XE that is submodular. It's supermodular essentially. Yeah. So this is, as I mentioned, submodularity versus. See, this is the definition of supermodularity and not submodular. It's like confusing this which one is this one. But generally, for both submodularity and supermodularity, for supermodularity, this is the idea that you will say that if I add a vertex X and vertex to a larger set, then the marginal gain that I have it would be greater than if I add it to a subset of this. This is the way to prove it, essentially. This is a much easier proof. For both submodularity or submodularity, this kind of marginal proof is much easier than this proof, essentially. But supermodularity essentially means that if I have S, a subset of T, and then I have some, and I, which does not belong to, so there is a vertex I does not belong to T. If I add I to T, the marginal essentially profit is more than when I add it to S. Then it would be supermodular. And you can prove that. So that we have it essentially for this one. This is for this set of things that for the edges that are inside here. Now, for the sets, we have this equality. So this is the things it is important. So for the sets, I have this one that essentially size of this plus size of B. I have in some sense modularity. I have it there. Good. So for the sets, I have modularity for this. like for this X, I have supermodularity. Now, when I have the tight constraints, what's the meaning of that? So if you consider two A and B that properly, they are essentially intersecting. This is called uncrossing argument. So if A and B are tight, now I can say that because I have these equations, and these are tight, then I can say that then it should be for the union and intersection also, they should be tight. Why? Because you can just get essentially write this one. These two are equal, these two equal, these are equal, and this is greater than or equal to this one. And so you can show that if these are not tight, then I get a contradiction. So just write this one and essentially this one. So essentially, this is the idea. Just considering the tightness and the fact that supermodularity of these functions x and the modularity of just the sets, because these sets, when they are equal, I'm talking about the size of the sets, then I can't just say that it is the case. So if two properly intersect, I can say that instead of these two conditions that properly intersect, put one which is inside, one which is outside. It essentially uncross them. You make it laminar. So you will continue until everything essentially so you start with some tight constraints and you will just uncross them. This number remains the same. At the end of the day, I have the same number of constraints. All of them are uncrossed. So almost all of these are using, this is a very substantial thing in all these proofs that we are talking about. Not only this, for the future ones. Good. Good. So now I am done essentially. Now, what do I do? This is so I want to essentially solve for now for just essentially spanning tree. So while G is not a singleton, I will solve the LP to obtain extreme points, remove all edges of 0 and contract all edges of 1, because 1 is should be in my solution. And essentially, I will continue this. Again, you can, in this case, you can use the same LP because it's the integrality gap. But sometimes you need to essentially, and means that if the solution inside, it means that contract it. Both endpoints make it essentially this. Good. Now, counting argument. So I want to say that there should be one variable, essentially of one value of at least one. Again, so it is not the case. So how many variables do I have xe? Because all of them are fractional, the same as before. No. So this is the token argument. This is actually one that, again, used a lot in the next ones. So this is the generalization of the previous. Here this is a double counting argument. I will give one token per each edge. And then collect one per tight set in the laminar family. I will show some leftover token. That is a contradiction. Because that says that the number of laminar families should be essentially, the number of tight sets should be less than the number of variables. Because I have some leftovers. So this is and this is essentially contradictory. So this is the token argument. I will give one. Now I will fractionally decide it, but I need to prove that I will give one to each edge. I will get it one from each tight set, and I say that some leftover remains. So it means essentially gets the proof for counting. Good. So let's go. How can we do that? So this is the fractional token redistribution. So far, we have done it essentially. This is more general than the previous approaches that we have. So an edge is in the support belongs to a set L in the laminar family. We always have laminar. It is the smallest set containing both endpoints of that. So here, for example, consider this one. This laminar family, at some point, this edge belongs to it. Good. At that point, that we say that this essentially edge belongs to that. So each edge, the first laminar family that both endpoints belongs to that, I will essentially consider that one. I will say that this edge belongs to that, and edge E gives xe of its token to the set it belongs to. XE, this is one token, it has it. Currently, this is actually gives just, so here it is essentially gives it to the one that, one other thing. It gives only its XE essentially. Good. So I know that each vertex has essentially degree 1 essentially for the things that we discuss again. But each edge here, it gives its token okay, each edge gives XE of its token to the set it belongs to that. Only XE. Good. How much is remaining? 1 minus XE for this, because one token it has. Good. XE part of it, only XE part of it, it gives essentially to that. But note that each edge had one token actually, because I want to give it one token. But only XE of it gives it essentially to this. What is the leftover is 1 minus X. So if I show that even with XE, if I just do that, then you can essentially get one pair each type set. I am already done. Because it means that all these XE should be either, essentially should be 1. Because if there is a leftover, then it means that I had the number of edges is more than the number of type constraints. Good. So let's see this one, then it essentially makes it clear. So, good. So let's, XE, this is the whole argument. So the XE tokens from edges that belong to a type set L can pay for it. It means that gives at least one unit to that. Good. Note that here, this is essentially the laminar family that we are considering. So in this laminar family, it may get XE from several edges. I want to that the sum of this XE that gets from the different edges is at least 1. It means that each type set, at least I can have one essential. So what is the argument? So note that what is first for the leaf set. So leaf set essentially has the leaf set has 2 essential, correct? At least 2 edges. In this case, X of S is equal to so if one edge belongs to that, then I know that X of S is equal to S minus 1, correct? So X of S means that this edge that belongs to it, it should be tight. So it means that essentially X of S, this E that I get it here, it should be the size of S, which is 2 minus 1. So it means that XE of this guy should be equal to 1. So this guy gets 1. The leaf. What about others? This is the idea. So I know how much this guy gets it. This guy gets X of S. So how much a larger set like this gets that has something? It gets X of S, all the edges inside, it gets essentially the X of E from them, minus those guys which are its children. Good? Because those guys, it does not get it. The XE of these guys, it does not get it. Anything even from this guy to this guy, it gets it. Good? So for the leaf sets, I mean, we know that X of S, it is equal. If there is a leaf set which is tight, it means that X of E is equal to S minus 1 because it's tight. It means that F of E should be 1 essentially. Now, for larger one, I know that, so this is the things essentially. X of S minus the X of its children. Good? Because, I mean, how much this set is getting? So this is, you see, this gets all of this XE, all edges that are there, it gets even these guys, except those guys that are belonging to these guys. Good. Now, this is a little beauty there here. The catch is that this should be non-zero. Why it is non-zero? Because if it is non-zero, you can say it can be the case. So if it is non-zero, it would be always this. If essentially it will be zero, it means that all these edges, it should be, if it comes out of this, essentially, it should be completely out of this vertex. Essentially, this is something you can just write it down, but it says that if this becomes zero, it means that this tight set, these things, you can write it as essentially summations of its children. So there should be something extra, essentially. It says that there should be at least one edge here that makes it essentially nothing. If all the edges are coming from his children and going out, essentially you can write this guy in terms of his children, and they are not independent. So this is again the same argument that you are doing. You need to just do it carefully, but we are doing it again. So you will do this argument. So they should be essentially this one. Now the other thing, it is non-zero, and also it is integer. That's another thing. Why? Because this x of s already, because they were tight, they were integers. So it is integer and it is not equal to zero. It means that it is at least one. Good. But I'm done because I know that each edge has at least a leftover of 1 minus x. So the number of constraints, the number of edges is greater than the number of constraints. This is the argument that comes almost in all of this. Because x of s, what was x of s and x of its children? All of them are tight sets. Tight set means that we have these conditions for
children, even laminar children, that's
laminar children. Yeah. Laminar tight sets as well.
Yeah.
So because all of them were integer, and this is not because independence is one guy here, it makes it essentially non-zero. Because laminarity, all of them are integer, and tightness. So it means that it should be this one is non-thing, so that is done. This is essentially the thing. Now let's this paper actually is from the JCM. I will just combine this argument with the same argument that I had it for this kind of jobs and machines to get this problem. Degree bounded minimum spanning tree. What is that? Now degree bounded spanning tree here. So the bounded degree spanning tree was the one that I just essentially discussed. I have the bounded degree minimum spanning tree. These are the constraints that I have it. Now I have for each vertex, I have also some tight constraints. Good. And here, these are some of them are called degree bounds. Some of them are called essentially spanning tree bounds. Now I have two sets of constraints that can be tight. Some of these or some of these. So this is the algorithm that I'm doing that. So I will essentially say initialize f equal to 0. Essentially, these are the set of constraints that I have. While essentially W is not equal to 0. What is this W? W is a set of constraints which are essentially the degree bound constraints that I have. Good. So W is a set of degree bound constraints that I have. I will solve the LP first. So I will solve the LP to obtain extreme points x star. I will remove all edges of x equal to 0. Then what do I say? So this is a JCM paper that actually this has the beautiful thing that they get the tight result of this one. So I will solve the LP. I will remove all edges of this. If there exists a vertex in W such that the degree of this is less than this, then remove V from W. What's the meaning of that? So you see, what is the degree of this? So consider this guy. This is the same as essentially this machines stuff that I mentioned. So this is this vertex V, and these are x of E, guys, that are attached to it. Here actually I don't. So you see, previous time I was talking more x equal to 1. Here I'm focusing more x equal to 0. I just removed them. Then what do I do? So this is some of this essentially E prime and E double prime. It is attached to this vertex. Say the degree bound of this guy was 2. Now, how many edges are attached in this graph to this guy is 3, correct? All others are 0. Note that all others are 0 because I removed them essentially. Or they didn't exist or I removed it because I will remove everything. So in this case, I don't need to put any conditions on V anymore. Correct? Why? Because those guys that I delete these edges x equal to 0, I delete them permanently. So before I need to say that the degree of V should be at most 2, correct? Now I have the degree of V is equal to 3, correct? But I will, if I remove that condition, how much I can violate it? At most by +1. So I just remove this condition. And again, so I will add this guy, I will remove V from essentially W, because for this guy, I know that the type, I don't need to put the type constraint, the degree bound anymore. I will do it until for no vertex there is a degree bound. At that time, I will find the spanning tree and I'm done. So what is the idea? The idea is exactly, now this is the algorithm. And what is the proof? The proof is, again, very similar to the previous one. So I will say that, again, you can say that when you are getting this one, the set of this would be essentially the tight constraints, those laminar family, those set of constraints. So let X star be extreme point, then it implies the independent tight sets. Independent tight constraints defining it form a laminar family L. And I have essentially some subtour. It is called subtour constraints, means these are called subtour constraints. And then I have some set of tight constraints in the terms of the spanning tree, and some other tight constraints in terms of degree constraints. And what was the idea is that so this is the idea that at any time I can just remove some x equal to 0, or I can find some vertex that I can relax its degree bound. When the degree bounds are all gone, I am done. Because then I just find the spanning tree and I'm done. The idea, again, the similar idea, assign 1 token per each edge. I will use xe of each edge token to pay for its laminar family. Now, use the remaining 1 minus xe over 2 for each endpoint degree there. Again, the same argument. And then say that all edge token used to constraints. So all edge tokens essentially are used for this independence L intersection T, because I have 2 types of constraints which are tight. And there are some left over and I am done essentially. So again, so here this is the whole idea is this kind of double counting that you need to do it. And how do you do this kind of fractional distribution? So here, I will give xe for that the laminar family, as I have mentioned before. Now, how much remaining 1 minus xe? I will divide it between these 2 guys, and then I will give it to each of for the degree constraints. Then I can show that essentially. So this I will do that. I will show these things essentially. And then I can say that from each, the rest is just some simple calculations. You can say that again, the similar things, because these are independent, from each laminar family, I can get 1 token because of this integral physics. I can show that essentially, this is also this token from edges incident to node T. I know that this one, because of the relaxation conditions, I know that there is no vertex that the number of this is at least PV plus 1. Because if it was there, then because of that conditions, I know that also I have this essentially 1 token from each vertex degree constraints. Again, why do I have it? I have just the tokens that each vertex gets is equal to sum of for all edges that it belongs to that. Yeah. So consider each vertex How much does it take? For all the edges that are attached to this, it gets 1 minus xe over 2. Sum it up over all edges. It would be the degree of this vertex because of this 1 minus b of v. This was because of essentially the tightness. And I knew that the degree of this guy minus this is greater than 1. Because if it was 1, I was just relaxing that conditions. So I know that the difference between the degree of the vertex, degree E means those guys that are, these xe guys that are attached to it, and all of them are fractional. Because I knew that the number of them was greater than its degree plus 1. It means that the difference between these two is at least 2. 2 over 2 is at least 1. So for each degree constant also, I will get it 1. Now, okay, all things that I have given for the edges, I could collect either from the, so I give it xe to these guys, then I could get either from this laminar family tight sets or from this, like the degree constraints. So far, there is no condition. What is the violation? The violation is that this degree constraints and this laminar family together, they also are not independent. So I get one more. So it means that I cannot have all L plus T. L is the number of this kind of laminar things. T is the number of things from the degree constraint. I cannot have all of them. These are all cannot be independent. One less, I'm done. That's the whole proof. That's the whole JCM proof. This was a stock paper, and this is a series of papers that they were improving. Like this plus 1, as I mentioned, optimal. I just get it. I just violated just by plus 1. This is essentially the best that you can do it, because otherwise it's NP hard. This was a series of work. The first guy said, okay, I can violate it log n or something like this. No, it improved to constant log n plus 2, 3. These are like a stock fox papers essentially. And then the last one was plus 1, and that is tight, and you can get it through this beautiful argument. So the last one that I wanted to mention also about this, there are lots of other things that you can get it essentially from the slides. Like for example here, about lots of generalization of this problem that was done essentially. The latest one was Singh and Lau, the co-authors of this book, that they could get plus 1 essentially. The people also generalize this one for other problems. This is for other problems. They have generalized it for Steiner trees and other things. Let me just mention some other other things. Also, the last one I wanted to just cover briefly. So the last one is this survival network design. What is the survival network design? You say that this is an undirected graph is given to me, and I want to find the minimum cost spanning. These are my demands. These are like the network flow that we talked before. So for each of these guys, essentially SITIs, I want to have at least RI edge disjoint path. This is called survival network design. It's the minimum cost that it has this. This is the work essentially. This is the great work by Kamal Jain. He first essentially used this kind of iterative rounding for this to show that when you solve this LP, this is the LP that you are solving for this, it has at least one edge of greater than 1/2. And then because of that, he could get a 2 approximation. But again, no one could use this approach. When I was talking, we said that it's like very general. We should be able to use for others. No one could do it until this paper of Moit, Singh, and Lau, that they could do it. And then using now, they could get the ideas and they generalize it for lots of other problems. The idea is very similar that he's doing. He's just essentially saying that this function, we had a supermodular. Here he says that this function that I have it, what is this function? This f of s. F of s is defined the maximum Ri. So consider any set S. Consider any set S. F of s is the maximum Ri's over all sets, over all SITI pairs that are separated by S. Good. Consider all pairs that are separated by S. What is the maximum Ri's for them? If you define this f of s essentially, you can say this f of s is SQ submodular. SQ submodular, it means that either this is a submodularity or this one. One of them is satisfied. Good. You do that, but both of them are integer. This is, again, when you consider in terms of sets, both of them are satisfied, like this one. So exactly using the same thing, you just write an LP. Then you will say, because it is strongly essentially submodular, you can just say the same thing that the whole thing form a laminar family. So he's doing this laminar family essentially. What is the algorithm? You will solve the LP if you will remove all XE edges essentially. Now, if there exists an edge in E that has XE greater than 1/2, you will add this edge to your solution and you will update the constraint. You know that this solution is there, so you will update this one to have, like, for those guys that you need to have this number of constraints passing essentially. By the way, what was the condition here? I think the LP, I need to say the LP as well before going to this one. This was the LP. So what is the LP for this problem? The LP is important. It says that X of, for any S, the number of edges that are going there at least should be this function f of s that I defined. Because if this guy has connectivity requirements, at least the edges that you can buy, it should be the number of connectivity that you need, the maximum connectivity that goes from one vertex inside S to outside S. So f of s is exactly this one, and this is the LP that you will write. So anyhow, you can show that this is also a laminar family. So the laminarity is essentially generalization of that. You are using essentially this one. It is called SQ submodular, but SQ submodular also is the same argument you can mention to say that this is laminar family. And then, as I mentioned, you will go, all edges of X equal to 0, you will remove them. The rest, you will just, if there is a 1/2, you will make it 1, and you will add this edge, and you will update these conditions. And then you want to say that there is one edge of at least 1/2. How do you do that? Again, you just show that these are laminar. I will just pass through that. Now, to show that essentially there is, so assume that there is no edge of greater than XE, the same argument. You need to do the token distribution. Consider essentially each edge. For each edge, you will give essentially, you will do similar things as before. 1 minus 2xe, you will give for the smallest set in the laminar family that contains both endpoints. Xe, you will get for the smallest set that containing U just alone, and xe, the one that the smallest set that contains V. You can essentially write this one. You say that I can just do it for each tight constraint in the laminar family. I can get 1. And there is always one edge with leftover that you can show that. So essentially you get the contradiction. And this is the, let me see what there are 1/2 things. Yeah. Yeah, this hence it is, yeah, so you can show, actually, this is the part. You can show that there should be a leftover because there is no edge that his value is at least 1/2. This is exactly the part. So because there is no edge that his value is at least at 1/2, then there is at least some leftover goes outside of these things, and then essentially you get it. So that leftover essentially gives this 1/2, becomes important for leftover. Anyhow, this is another things you can just go through that and read it through the slides, or just read from the book. The books that I have mentioned. So the book that I have mentioned, this is the book. I think this is a great book. You can just read it. Some other problems that it has been solved. It's not a very long book, but it's beautiful. And you can see all the details. And there are some open problems still there, especially as I mentioned, for packing constraint, packing problems. Sometimes packing and covering, we can solve it. But generally, some packing problem, we don't have any approach of using this kind of iterative rounding. And it would be great to solve them. And this has been, so far, has been used for lots of other problems. These are, you can read it from the book. So for this is the best example for bipartite matching, a spanning tree, and others. This is for base problems. These are like the important problem that you don't relax. And these are essentially for the problem that you can do the relaxations. This approximation and relaxation, these are degree bounded, partial, essentially survival network design with degree flow and other things. Lots of problem now you can do it. Before we didn't know that, as I mentioned, Kamal Jain has done it, then Lapchi-Law and Moise Singh has done this one, and then all of this we know. And you can read all of them from this book. Okay, I'm finishing here.